Hello everyone and welcome back to this series of lectures on efficient LLMs. So let us continue our discussion on efficient training versus inference in LLMs. So in the last lecture there were a lot of very basic doubts. So I wanted to ask a very basic question and start with that. Right? So the question is, what is it that we are modeling in the language model? Right? So I'll give you an example. So example, if I have a computer vision model which is doing classification, right? I am modeling P of the class given the input image X as a parameter theta. Right? So it's essentially a discriminative model which is giving me P of Y given X for all Y belonging to the classes. Right? This is what we can get, and this is parameterized as theta. Now, in a language model, what is it that we are modeling? When I say P theta of X, or when I say M theta of X, M is the language model. What is it that I am computing and what is it that I am maximizing? What is it that I am modeling here? So in general, in a language model, what we are modeling is the language, which essentially means that if I have a model P theta and I randomly get any sentence X, which is a sequence of, let's say, X1 to X T. For example, let us restrict our understanding to fixed T number of words, right? Now, if I have 50,000 words in my vocabulary, right? This is the size of my vocabulary. How many such sequences are possible here? At each position, at each word, I have 50k choices, right? V choices, and therefore I have V to the power T choices. These are the total number of sentences that I have. If I have a random model, it will assign almost equal probability to all of those. But all of these are not, valid sentences in a language, be it English, be it Hindi, be it a programming language, right? So what we are modeling is that we want our parameters theta to be such that the probability it assigns to a sentence is high if X is a valid sentence. This is what we want to model in a language model. We are modeling the language. So our model should assign higher probability to sentences which are valid. This can be done in an encoder only model. This can be done in a decoder only model as well. Right? Now, how do we model this? Now, that is a modeling choice. Right? In a decoder only model, we factorize this distribution as a conditional distribution, as in we say that this is equal to P theta of X. I should not use small letters. That is for a specific sentence, whereas when I'm using capital, it is a random variable. So X is a random variable which is t dimensional, right? So the way we factorize its probability is, we say that this is equal to P theta of X1 into P theta of X2 given X1 times P theta of X3 given X1 and X2, and so on and so forth, Xt given X1 to Xt minus 1. This is a modeling choice that we are making, right? And by virtue of this modeling choice, we are able to find the next token prediction as well, right? So the transformer model, when I pass this X as an input to the transformer model, I want to compute P theta of X and maximize that. And the way transformer model computes, a decoder only model computes it, is by factorizing this probability in this fashion, right? So we get the P theta of X1, right? We get P theta of X2 given X1 as well simultaneously. Why are we getting it simultaneously? Because the way we are modeling it, by the virtue of tensor multiplication and self attention, right? We can do it. In order to compute the last token's conditional probability, we don't have to wait for computing the previous token's probability, right? We can do it in parallel. Is that make sense? We are not generating. Let's stop here, right? We are talking about training. I'm saying I want to maximize my theta in such a way that it maximizes the probability of valid sentences. And a decoder only model, right, factorizes it in this way. When I pass it through the transformer layer, right, I get all of these probabilities simultaneously. Now contrast it with RNNs. Have you covered RNNs? Is it possible to get these simultaneously in RNNs? It's a sequential process, right? And why are we able to do it in parallel? Because of self-attention, right? Because the way this it is happening, you can think of it as a graph neural network as well. At each layer, right, I have token 1, x1 to xt. Now I have small letters here because these are specific words, right? This is not a random variable. I'm representing a specific sentence here. Xt, right? So this is let's say at layer 0, I have the embeddings of all of these tokens. Layer 1, right, is looking at or is attending to the embeddings of these tokens that we computed in layer 0 as the output of layer 0, right? As the output of layer 0, we got the token embeddings, right? We got the token embeddings, we processed them through KQV, and then this last token is attending on all of this and computing its output probability, right, or output embedding. And this token is attending to all the previous tokens. And because of self-attention, we are able to process all of this in parallel in one go.
This is true only for the training.
This is true only for the training part. We are at the training part only, right? So now let us look at, how does a forward pass looks like in a toy language model, right? So we have the embedding layer initially. We have transformer layers here. We have, let's say, number of layers is 32. We have 32 transformer layers, and in the end we have an LM head which will map the token embedding to a probability distribution over V size, vocabulary size, right? And in the forward pass, this input IDs is a sentence X, which will be equal to x1 to xt, right? And we first get the embedding of each of these input words through this layer. Once we have the embeddings, we sequentially go through all the layers, right? In the end, we get the embedding at each position. We pass it through the LM head to get the logits. So what would be the size of the logits here? It is going to be T cross V at each, and what is it? What does it represent? At the first position, which was, let's say, beginning of sentence, it represents the probability of the next the word at position x1 given BOS, right? So this is the entire distribution, and we look ahead, we teacher force, and see what was the first word. So the first word, for example, is the cat sat on the mat. This was our sentence. So the first word is the. When we initialize weights randomly, this distribution is going to be uniform. After training, the probability of the is going to be very high, right? And right, so
I think all of these probabilities are
during training, yes. In one forward pass, we get not only this, but we also get this distribution as well, which, let's say, represents the distribution at position sat, right?
Like for first iteration, let's say the probability of B is 0.5, and
Okay.
then in next iteration, so will the probability still remain 0.5 or will it change to 0.6?
Right. So what do you mean by iteration here?
So once all the inputs have been through all the layers.
So what is one input in your case?
So here it is one sentence.
One sentence, right? So So one sentence is the input here. When it goes through the model once, model would have adjusted its weights to increase the probability of that sentence. Let's say I overfit on this. This is the only sample that I have in my training data. Let us assume that. So I run this forward pass 1000 times, and then it has overfit on this. Now when I pass the partial sentence the cat sat. Let's say I pass this through the model, right? When I pass this through the model is going to give me the probability at BOS. It's going to give me the probability for the token the, right? It will be very high because this is the only sentence that we have trained it with, right? And again, because the model does it in parallel, right? Because of self attention, here also we will have a distribution when we do the forward pass, right? What would this distribution look like? This distribution corresponds to the embedding of the word sat, which has been created using the tokens that it existed prior to this, before this. And when we were training, how did we modify this distribution during training? When we were training using this sentence, right, the cat sat, the output had a distribution at each token, right? This is for the cat and sat, let's say. Here, when we were processing the token the, this distribution was changed so that the probability of the word cat, let's say this is cat, let's say this corresponds to cat, this is maximized. And when we processed the sat, when we got this distribution, how did we what loss did we compute using this logics? So when we train, what is the loss that we use? Right? Yeah, and at each token, the loss is the cross entropy loss, where we maximize the probability of, in this case, here we will maximize the probability of the token on. Wherever the token on lies, whatever is the probability, we would have maximized that. Now, once the model is trained and I pass this sequence, the cat sat, through this, in the end I will have a probability distribution. How should this distribution look like? I have trained the model. Yes, so the token on, right? So this is on the token on, we will have a very high probability, right? So this will have a very high probability, let's say 0.9. And how do we use this model for training? Okay, we say that, okay, now this is the highest probability token, let's pick that, and this becomes my next token, right? So my sentence now becomes the cat sat on. Now how do I get the next token? I can pass this sentence as well, right, through the model. In the end, I will again have a distribution over V size, and then here the will have the highest probability, the token corresponding to the. I will pick that, and now this becomes the input, right? And when I pass this through the model, I will again have a distribution, and here which token will have the highest probability? Mat. And now if, let us say, in addition to this, I have another sentence which is the cat sat on the table, and I am training using both of these, right? Then at this position, when I am processing the token the, which has to give me the probability of the next token, both mat and table will have high probability, because that's how I have trained the model. Sometimes I am asking it to increase the probability of mat, sometimes I am asking it to increase the probability of table. So both will have high probability, let's say 0.4, 0.4, for example, right? Now which one should I pick, right? While generating, it's a choice. I can either pick the one which has the highest probability, let's say one is 0.41 and the other is 0.4. I can either pick 0.41 or I can sample from that distribution, right? And that is called sampling, right? Is this part clear? Because this is how we motivated by, all the efficient implementation that we are doing during inference, we motivated it by this.
So during each pass, we are passing the entire sequence.
Yes.
We are trying to compute the loss.
During training, we pass the sequence only once, and we get all the distribution, that every token.
So then in each pass we will be updating that probability for each token, right?
Yeah, we'll be maximizing. So our loss essentially is gonna be, so we will get p theta of x1 given BOS times p theta of x2 given BOS and x1. This is the probability of the sentence x, right? And if I take the log, it's going to be log of this plus log of this plus log of p theta x t given the previous, right? And if I'm maximizing this, then I'm maximizing the sum of these, right? So so automatically at every position, the conditional distribution that we have, we are trying to maximize that, not individually, but at a collective level. I mean, for the entire sentence. Right? And because of the way we are factorizing it in a decoder only model, we are able to use it for generation. We cannot use an encoder only model for generation.
So, in encoder only models, we have either mask tokens or mixed sentence prediction. Let's say in that case, it's basically major differences by. So essentially, if we look at it, to say we are trying to predict the mixed token given the previous, right?
Yes.
If we see it from then it will be predicted based on the next one.
Which we don't have.
Yes.
So therefore, we cannot use it for generating the from left to right. I mean, if I can very well train a model from right to left as well. I can factorize it in the reverse order as well. I can always say that it is p theta of xt times p theta of xt given xt minus 1. Sorry, xt minus 1 given xt. Right, the other way around. We can do that. That will be a perfect language model, but it cannot generate from left to right. Right? It can. Why can't we generate? Because in an encoder only model, if I have x1 to xt as my token, right? Let's say the same example, the cat sat on the mat. The way I am, modeling the probability for this token, and right, it is dependent on all the other tokens in the past as well as in the future. And I cannot compute this with only the past. I need to know the future as well, right? So we can't generate.
How did it change if we move to encoder decoder?
Yes, so encoder decoder is fine. It's perfectly fine. It has a decoder component which will generate. So the idea of encoder decoder is that there is some input on which you have to always condition, right? So the input that you have, x1 to x, let's say, how should I call it? So I'm using the word I input, I1 to IT, right? This is, let's say, the question: what is the capital of India? Right? Now, to understand the question, because it is given, while I am encoding the word capital, I should exploit what is there in the future as well, right? If India is there, I should, it will be much faster if I can look. I don't have to wait till the sentence ends to get a meaning of the entire sentence, right? So I will be able to encode the knowledge in the input through a bidirectional, through bidirectionality. I mean, each token can look into the future as well, future tokens as well, right?
But we are still able to do that in decoder.
We are able to do that. We are able to do what in the decoder only model?
Like if I get some input for the decoder model,
Yes.
then that is my previous context of the previous tokens. Based on that, I will integrate the next.
Yes.
So how is that different from this?
See, this is the encoder part of encoder decoder. In the decoder part, the way decoder works is that it only looks at the past, right? The decoder part is able to generate the model. It's not the encoder part which is generate the text. Encoder is encoding the question, the input,
question is like, if we look at the encoder decoder model,
Hmm.
we have close attention basically
Yeah.
attend to the encoder.
Yes.
And on the
Hmm.
the next token have to attend to
Previous ones. Yes.
so there is a principle of the previous tokens.
Yeah, all these are previous tokens. Yes.
Then the next token will be based on this.
All of these. Right. It will attend on all of these.
How is that?
So I'm failing to understand your question. Is your question how is encoder decoder different from decoder only model?
My question is basically,
Huh?
so my question is basically, in both the cases, it will be able to predict
Because by the virtue of the decoder, BERT cannot generate.
but can't.
Right. So decoder, because of the decoder, it's the decoder part which is able to generate. It's not the encoder part which is able to generate. Encoder can be used for other discriminative tasks like classification, for example.
So what? Yeah. So that's my question. Actually,
Huh.
what is the use of the encoder part?
Okay, so that is why do we have encoder models, right? So I mean, this is the evolution that's how it happens, right? There are certain tasks, for example, machine translation, where we know what is the input, right? So the initial models that were created for tasks like sequence to sequence mapping or machine translation is an example there. Encoder decoder models were created because it makes more sense, to exploit what we already know, which is the input sentence, right? So they try to get the information from the encoder from the input through the encoder only model, which is much more efficient than the decoder only model,
Why is that?
because it can look into the future as well.
But if it look at the decoder model also, then what? The position of India.
At the position of India, we are able, yes, but the token embedding here, capital, is not aware of what's gonna come, right? And while translating, if I may need that information here as well. That information might get useful. We don't know, right? For the task like machine translation, right? And eventually decoder only models prevailed, right? I mean, we have been able to scale them up, and we have been able to improve the performance so much that encoder decoder models are out of fashion now. They're not being used, right? And why should that be? I don't know why should that be, but one intuition could be that we are training such huge models with such huge data that maybe this constraint of the decoder only model, that you're not able to look into the future, is acting as a regularizer. Some sort of a constraint onto the model architecture itself. Even for the cases like machine translation, where we have the input a priori, we know that we have the input a priori, right? So that is one one conjecture. I don't know, right? So okay. So is this part clear? Because this is crucial, right? Okay, so with this toy LM, how does the training loop looks like? We get one sentence from the data, we pass it through the model, we get the logits. These logits are modeling p theta of x1, p theta of x2 given x1, comma, and up to p theta of xt given the entire sequence till xt minus from x1 to xt minus 1. We have all of these probabilities, right? Multiplying these gives me the probability of the sentence, and that's what we try to maximize. We compute the cross entropy loss between the logits and the labels. And what are the labels? For the token the label is gonna be the cat sat on the mat. For this token the, what is the label that we have? When we compute cross entropy, we will get the logits from this position, right? So what is the label against which we compute the cross entropy loss? No, the label is the prediction. The cat, yes, this is the label. So this is the label, and this is the input, right? So we shift. I mean, this entire sentence shifted to the left becomes the label. All right. Now I have put the forward pass here for our reference, and as we discussed, if we have to use this model for inference, which means that we can, because it is a generative model, we can use it to generate text, right? So a naive way of doing it, what it will do is that I pass the entire input IDs through the model, I get the logics, right? I get the next token, which is from the last logit, right? -1 will give me the last logit. I do argmax, greedy decoding, and if the next token is end of sentence, I break, or if otherwise I just append it to the input IDs and pass it in the for loop. And what we did in caching was we observed that there are some redundant operations that we are doing. We don't need to compute KV keys and values of the tokens which we have already processed, and therefore that's how we motivated caching, right? So okay, so we covered this last time. And the other thing that you guys asked me to revisit was blockwise self-attention computation, right? So let's look at it with an example. Let's say the input is the key difference between LLM training and inference. This is the input, and I want to compute the self-attention, right? So I have the keys for all and the values for all. So these are the values of each token. This is the keys, and let us say I'm computing it for the query Q8, right? Blue color I'm using to represent the HBM memory, which is 80 GB, right? And this is the expression that we want to compute, which is e to the power Q8 transpose or a dot product of this with K1 times V1, right, plus e to the power Q8 times K2 times V2 up to e to the power Q8 times K8 V8 divided by, so these are the softmax weights divided by summation over all these exponents, right? This is what we want to compute. So I've put it here, and the way we want to do it is in a blockwise fashion. I want to first compute this over a block, the first block, let's say K1 to K4, using the query Q. I get the scores. So the score is Q8 dot product with K1, right? I exponentiate this e to the power Q8 dot K1, right? And then I multiply this with the V's. I get this A1 times V1 plus A2 times V2 plus A3 times V3. I get L1. I put this L1 back into the memory HBM. So all of this ping is being done in the SRAM, right, which is fast. And notice that we are not storing the attention. We are not materializing it in the blue boxes or in the HBM. We store L1 here, and in addition to that, we also store O1. So O1 is the output vector, which is computed using softmax over these four. And in addition to this, we also need the sum over the denominator that we have, right? So this is the denominator, right, that we use. Similarly, we can do this for the remaining four, right? We get L2 and we get O2. Now how should we combine these two to get this expression? Come on, let's do it together. Tell me. These are the vectors. In the numerator we have vector, and the denominator we have a scalar, right? What is the denominator? Here, let's first get the denominator. The denominator is sum over all the keys, right? Similarity of the query with the keys, right? So what should this be? Using these four numbers, what should be the denominators? L1 plus L2, right? So this is L1 plus L2, right? What would be the numerator? O1 L1 plus O2 L2. Cool, right? So we are able to split the attention into blockwise computations, and this is what paged attention does. We have the first block, right? We have the second block. We have this query. We can compute the attention using the first block and the second block, right, in parallel, and then we can combine them, right? Okay. Now, what if I don't want to compute it in parallel? Let's say I want to first compute this. I want to load it in the memory one by one, in the SRAM one by one. I don't have sufficient SRAM, and that is what flash attention does, by the way. It loads first KV block corresponding to this, right? It keeps it in the memory, right? And in the inner loop, for each query, it computes L1 and O1 for each query in parallel, because it can parallelize tensor operations. It can give it to multiple threads. K and V's are loaded once in the memory. In parallel, it computes L1 and O1 for all the queries. Now, let's focus on only one query for now. I have computed this now, and this is in the SRAM. And using the second, I load the second block in the memory. I compute L2 and O2, right? I don't want to keep both of them in the memory. Can I update? So this is the space that I have reserved in the HBM for these two variables. Can I, how should I update these two using this? I want to maintain, the idea is that L1 and L2 here were the attentions of individual subsequences. Now what I want now is that I have computed L1 and O1 for a subsequence K1 to K4. Then I load all of these, the second block, and when I'm updating, I'm putting on the HBM, I want to just update these spaces that I have. I want to have L only and not 1. I just want to have L and O. Right? I want to use these to update my L's and O's. Right? How can I do that? My L would be L plus L2, the local variable that I computed here, and my O would be L into O plus, yeah, so exactly L2 into O2. So this way I just maintain L and O in my HBM and I keep on updating it. Right? And this is exactly what flash attention does. Right? Load 1 K and V in the pink memory, which is fast memory. Keep it there. Parallelly compute for all the queries, right? And write in their corresponding L's and O's. Load the second block of K and V. Parallelly compute it for all queries and update the respective memory in HP. Right? Okay. So yes. So now there is a lot of homework that you have to do. You have to, read about safe softmax. The way we computed has some numerical instability. So you have to read about this, and then you have to read about the concept of tiling. We simplified a lot of things here, right?
So they were using some concept of maximum softmax.
Yeah. So yes, so that leads to safe softmax, and this concept is not new in general. Also, when you do softmax, right, or log softmax, those things are used. That is not new to flash attention. That is a standard thing. And why?
Like what is the use and purpose?
Yeah. So the idea is essentially numerical stability, and the problem is that in softmax we are computing exponents, right? Now let's say my attention scores are 1 million, 1 million and 2, right? 1 billion, or let's say 900,000. These are my attention scores, right? Of the order of 10 to the power 9. Now when I do e to the power of this number, it's going to be really highly unstable, right? But when I'm doing softmax, does the absolute number matter or the relative numbers matter? If I have 10 to the power 9 versus 10 to the power 9 plus 8, let's say the other one is this, right? It's the difference that matters, right? So in order to avoid computing the exponents over very large numbers or very small or very large numbers, now, right, they first figure out what is the maximum that is there, right, and then they subtract that maximum from all of those so that everything is in the same range, right? Cool. So if you implement these things on your own, you will realize, right? Otherwise it's difficult to remember. Okay, so this is this, and yeah, so this is where we left. We were talking about VLLMs, and at a high level, VLLM has 3 or 4 major components. One is a front end, which could be also a CLI, right? You can simply launch a VLLM server, through a command line interface. It has, to manage big models, it has a distributed model executor where it is at the back end. Essentially, it is using tensor parallelism on a single node and pipeline parallelism across nodes, right? And then there is a scheduler which will schedule or route different requests, and then you have a block manager which will manage the paged attention stuff, right? Okay, so yes, so now this brings us to another homework which is in continuation of efficient inference part. We could not cover flash decoding, right? And we could not cover speculative decoding. So flash decoding essentially means, so when you look at flash attention, as we said that the way flash attention works is that they load one block of k and v in the memory and parallelize across all the queries, query 1, query 2, query 3, query t. All of these are computed in parallel, right? And once for one k and v, and then next k and v are loaded in the memory, and then we process q1 to qt in parallel, right? Now when you're decoding, you have only one query for a batch. So if you use just this flash attention, this parallelization, you'll see only 1% GPU utilization. Everything's going to be empty, right? So they modify it a little and they come up with something called flash decoding. The idea is what we looked at in the block decoding, that you have k's and different blocks of k's and v's, right? So you can parallelize on the dimension of k's and v's, right? So you parallelly compute for all k's and v's. Let's say I split my kv's into 5 blocks, right? K1 v1 block 1 and K2 v2, K3 v3. I load all of these simultaneously in my SRAM, right? And each core will be working on each of these blocks. I have the same query q, and I compute the flash attention of q over kv the way we were doing it in the block attention, right? All across in parallel, and once I have the output, I can combine them. I will have O1 V1 here, which I have to put in the H. Now I cannot do it because I'm not doing it sequentially. I'm doing it parallelly. Therefore, I will store O1 and V1 in the HBM, O2 and V2 in the HBM, and O3 and V3 in the HBM, and then combine them. Right. So this is what flash decoding is. Speculative decoding essentially means that you can make a guess somehow. Let's say I say the cat sat. You make a guess on the mat. Somehow you are able to make a guess, right? Now, can I verify all of them together? Because I know that a forward pass can process all the tokens simultaneously. If I make a sentence, the cat sat on the mat, complete sentence, and I pass it through the model, can I if it passes, then I'm good. I got in one step, I got not one but more than one tokens, right? So that is the idea of speculative decoding, where you guess and then verify. So so this is, and I will not go into much details here. And there is one more important piece that we have to cover, and we have to finish it today, right? Which is the third part. Recall that we talked about efficient training because we wanted to train huge models. Requirement was million GPU hours. We cannot do it serially. We talked about parallelism for scale, right? And then we saw that two models had different throughput. Right, they were similar size, mainly because of the efficient implementation in one of those, where we covered flash attention, Liger kernels, and then we saw that throughput is related to inference, right? You measure throughput during inference. So what are the efficient inference techniques that are available? We saw KV caching, paged attention, and we have left flash decoding and speculative decoding for homework. Now the third part was, again, recalling this graph where we are measuring throughput versus the performance. We saw that there are these two models, right, which have similar performance and much different throughput, much higher throughput, even though the model size is bigger, right? It's roughly 56 billion, this is 33 billion. So how are we able to do that? And the answer there lies in the efficient design of this model, which is mixture of experts, right? So that's what we will cover in this part. And to motivate that, let's first look at some interesting study that happened in 2020. This is called neural scaling laws. So what it says is that the bigger the better, meaning if you have a bigger model, you will have better performance. Right? So in this graph, for example, you have on the x-axis the size of the model, and this is the test loss on some test data, and they are showing that it follows a power law, right? So the loss is alpha times x to the power beta. This is the power law that they're fitting, and they show that if the model size increases, the parameters, the performance improves, right? And this is true for not just the model size but also for compute and data set size as well. As we train on more data, performance improves. As we are allowed to compute more, performance improves, right? But then again, going back to the first slide that we had, this 75 billion, almost 75 billion model takes 1.75 million GPU hours, right? Now there is a model switch transformer which is 1.6 trillion. How much time will it take, right? At least 5 to 6 times of this. So what should we do? We want to increase the model size because we know via neural scaling laws that if model size increases, the performance improves, right? Now we want to increase the model size, but that is going to take a lot of time to train. So what should we do about it? Okay, so is there any efficient way to increase the model size? And to answer that, let's look at how we use LLMs, right? So we use these LLMs and we train it for multiple tasks, right? We are doing it, it's the next token prediction during pre-training, but when we use it for summarization, we use it for coding, we use it as a question answering agent, and so on and so forth, right? Now in general, when you train a model for multiple tasks, what is it called in classical ML? Multitask learning, right? So where you are creating one model for multiple tasks. And how does a multitask model architecture looks like? Typically you have a lot of common layers. The input passes through the common layers, and then you have task specific parameters. So here also, if we know for which task this input is, right, we will go through all of these common layers, but we will route it to one of the heads, right? So this is, and so only these will be active. We will have activations for only these. Although the overall model size, it has three such heads, right? If we look at the parameters of the head, we have 3 times, we have increased it by 3 times, but when we are using it, it's going to be the computation and activation will be only through 1x, right? So, but can we use it directly here, this architecture? No, because I mean, when we are training multitask models, we generally in our training data, we know what is the task here. The input is x, comma, task ID. And that's how we route it to the specific head, right? But we don't have this. We don't have this when we are training language models. So what is the alternative, right? So what should we do? And in contrast to this, we know that in LLMs, our LLMs looks like only this. It doesn't have this part, right? All the layers are active. All parameters are active for all the tasks. But then where should we introduce this sparsity, or where should we introduce this multiple heads in the language model? Right? So this is the question that we have to answer, and the answer lies in mixture of experts. It's not a new idea. Just like multitask learning architecture, there is a standard multitask learning architecture. There is a standard architecture for mixture of experts model as well. First published in 1991, right, by the Jeff Hinton group. and let's first visit that. How does it look like? We will integrate it with transformers later on. Let's first look at how does a mixture of expert model looks like. In a classical neural network, you have an input X that goes through one neural network. Let's call it expert now. It goes through one expert and we get the output. In mixture of experts, what do we want? We want multiple experts, right? And we want to route this input X through one or many or all of these experts, depending on how we model it, right? But how do we decide that? How do we route? We don't have that information, and we only have input X. So what should we do? Anyone? Any guess? Routing to all, and then see and make a prediction from all of those.
The better one will be, and this input will that input
Right. And so this could be one strategy, but then all of these are randomly selected. How will the allocation happen for the first one? Randomly, and it may get you into troubles. It may. Let's think about it. Right. Another alternative is, can we learn to route? Right. Gating, right? So let's include a gating network into our model. This is nothing but a W. We are learning it, right? WG. We pass X through it. It will give me a probability distribution over all the experts, right? Let's say GX2 and GXN minus 1 here. I'm highlighting 2 experts for now, right? And so let's say we select these 2 experts using some mechanism, and we get the corresponding outputs, right? And we take a linear or convex sum of these 2 using the corresponding probabilities, right? So this is the expected value. This is the expected output that I have, right? So one expert is giving me yn minus 1 as the output, the other is giving me y2 as the output. The expected output is the corresponding probability times that, right? And depending upon how we model, if we don't care about the computation cost and we just want to increase, we want to use it as a modeling choice, we can have all the experts as active. So this gating network will give me a distribution over all the experts. I get the expected output, which is probability of selecting the first expert multiplied by the output from the first expert, right? And this probability, this gating is a softmax over, this is just a linear layer. We have this learnable parameter WG. This is getting trained along with all the expert layers, right? Okay, cool. Now, let's look at a quick chronology of mixture of experts model. So they were first introduced in 1991 by Jeff Hinton. Then they were first used in deep learning in an LSTM architecture by Eigen et al. In 2013. And then in 2021, we got first MOE layer in the transformer based model. This was switch transformers. And then came Mixtral, which was when it came, it was a small model as compared to its competitors, and it was able to beat many of those. And then recently we got GPT-4, which is also a mixture of expert, DeepSeek, and Minimax models, right? Okay. Now the question is, where should we use this mixture of experts? So now we got the idea of mixture of experts. We know that there is an architecture called mixture of experts. Now how should we integrate it with transformers? Where should we use it? Where should we insert this MOE? Any guesses? This is how a transformer block looks like, right? We have self-attention, normalization, feed forward, and then normalization again. Add and norm again. The feed forward layer, right? So this feed forward layer, recall that self-attention is the one where tokens are interacting with each other. X is going to be x1 to xt. In self-attention, they are going to interact with each other. Whereas in feed forward, right, it's an MLP. each token is processed independently, right? So each token is if I call this as an expert, then each token is routed to the same expert, right? So let's try to replace this with a mixture of experts, right? So let's take an example. Let's say my input is only 2 words, more parameters. Yeah.
What exactly we mean by expert? Because if we get multitask, then specific task we say expert.
Yes. Yeah. So we cannot assign any semantic meaning to it, right? It will automatically learn and share the task. So there is no, I mean, I cannot say, although there are some analysis paper, we cannot say that this expert is doing coding, this expert is doing machine translation, and so on and so forth. We don't know that. And the assignment is also, learning. We are learning the gating network as well.
Essentially, it's like
It is a feed forward layer, but instead of one, we have many, and each token will choose where to go, which one to pick. The gain is that we are able, we motivated it by saying that we want to increase the model size. So we replaced one feed forward layer with 8 feed forward layers, right? And intuitively the gain is that we are increasing the capacity. It may happen that model automatically learns that expert 1 is for coding, expert 2 is for machine translation, expert 3 is for summarization, and so on and so forth. We can only hope, right? But at least now the model has the capacity, right? And that's the whole idea, right? We modify the architecture according to our intuitions and hope that model will capture. Now the model has the capacity to capture our intuition, and learnability also improves from that perspective, right? Otherwise, a 2-layer MLP is a universal approximator, right? But the learnability is the issue. Okay, so the way it looks is that both the tokens, more parameters, interact with each other in the self-attention layer. We do add and norm separately for these two, and then we have a router which will decide where to route this token more and this token parameters. It will be different for both. So for example, here it routes to feed forward on the second expert with some probability 0.65, and it routes to the first expert with probability 0.8, right? We multiply these two and we get pass it through the forward layers, right? Okay, so this is the MOE layer, and how are we able to reduce the computation? Here, are we able to reduce the computation? The computation is similar, but model parameters have increased, right? So if there are, recall how many parameters are there in a feed forward network? We have 4h square, the first h to 4h, and we have another 4h square. So 4h to h, this has 4h bias terms and this has h bias terms, right? So this is 8h square plus 5h, versus in attention we have KQV3 mappings h square plus there is a projection layer where we concatenate all the attention heads output and pass it through a linear layer, which is 1h square. Right? So this is 4h square. So most of the parameters are here, it's double, right? 8h square versus 4h square, right? And we are able to, with let's say 10 experts, we are able to make it 10 times 8h square, right? We have been able to increase the model. Capacity of the model has increased, and during training, computation remains the same, because each word is routed to only 1. In this particular architecture, we can route it to 2 as well, or 3 as well, or top k as well, right? In general. And yes. So, okay, this is the, and so that's why they're called sparsely activated MOE transformer layers, right? Okay, so the MOE layer, and yeah, so I will skip this. You can go through this yourself. What essentially we are saying here is we are computing how the gradients are gonna flow through the router and through the parameters here. We need to train the router here as well, right? We need to train G of X. We need to train there is W here, right? This WG, and we need to train the parameters of FFN. We need the gradients through both of them, right? So this is simple chain rule. Let's skip this for now. But then we need to address some important questions, which is why are these experts not collapsing in practice? We are starting them randomly. This is the question that I think I raised earlier, right? It may so happen that all of them learn the same weights, right? So what is preventing their collapse? So there was a paper which tried to study this systematically through synthetic experiments. What they did was that they created synthetic data. They created this data. There are two classes, positive class and the negative class. There are these four clusters. The data is divided into four clusters. We can see that this part is separable linearly, this is separable linearly, this is separable linearly, and this is also separable linearly in the higher dimensional space. This is a two-dimensional projection, right? So we know that there is a mixture of expert model which can, with four experts, this is expert 1, this is expert 2, expert 3, and expert 4. So if I train an MOE model with this data, this is what I expect it to learn, right? Okay, now they first tried with each expert being just a linear layer, W E I times X. This is the linear expert that they first trained, right? And they observed that it doesn't learn anything. Now let's try to understand this graph. Color represents that when I pass this data point, this is the data point for classification to the MOE model, right? To which expert it goes. So each color represents a different expert. Blue is one expert, green is another expert, red is another expert, right? What am I expecting? I'm expecting that this should be, all of these data points should go to one expert. Let's say blue. I want all of these to be blue. I want all of these to be green, let's say. I want this to go to blue expert, this to green expert, this to red expert. But what we see is that the points here are going to all the experts, red, green, blue, yellow, right? So this is the problem. And when they introduced non-linearity in the architecture, that solved the problem. That with the non-linearity, when they train it, they see a very clean distribution, right? That all the points here are going to one expert, and that is what we wanted, right? So they try to motivate it. They say that when we have just a convex loss curve, which is in the case of a linear classifier, even if we start from different points, because of the shape of the curve, it kind of they all collapse to the same parameters. And when we have non-linearity, the loss shape is non-convex. Even if we start with the same parameters, the non-convexity of the loss curve will push them in different directions. So this was one analysis that they did about why these are not collapsing, right? Okay, so we saw that with the mixture of expert models, there are various pros because of which we selected them. The first one is that we are able to increase the model size, right, by the number of experts that we have, and the computation remains the same because we selectively route to only one of those, right? And because of which we get faster inference and efficient pre-training as well. But there are some issues as well, right? I mean, there's no free lunch. So we have 10 experts. Will they fit on the GPU, right? The model size is going to increase. We looked at, the first part of this lecture series focused on managing the memory of the GPU. If we increase the model size beyond a point, this GPU memory of one GPU will become insufficient, and we have already looked at various tools to tackle it. We looked at data parallelism, tensor parallelism, context parallelism, and pipeline parallelism. Which of these can be used in this case? Can we use any of these in this case? Right, so we can, but pipeline parallelism can always be used, yes, because we will have different layers on different GPUs, and we can always use pipeline parallelism. Cool. But then we define a new type of parallelism by because the architecture is like that. You have separate experts, they don't need to sit on one GPU. They can sit on different GPUs, right? So this is the fifth dimension of parallelism that we did not cover earlier because we had not looked at mixture of expert model. So this is expert parallelism. In one GPU, this is the MOE layer. All the experts are sitting on one GPU. We split them. We split them on multiple GPUs, and combine it with, let's say, data parallelism. Right now, in data parallelism, both the GPUs, recall what happens in data parallelism. What is different and what is same? Data is different, model is same, right? So we have we have different data points. We have a sequence x1 and we have a sequence x2, right? Some token of this sequence, right, let's say xi, gating may decide that it needs to go to this expert, right? And some token here, similarly, x2j may have to be routed to ffn1, right? So this requires communication across the GPUs, right? So this increases, of course, all-to-all dispatch and all-to-all combine, but we can't avoid that. Okay, and this. Here we saw that we're using it in conjunction with data parallelism. We can combine it with other parallelism strategies as well. Okay. Now, one issue that we tackled earlier was that of expert collapse. That the experts collapsed, right? But what if the router collapse? Meaning, the gating network is also learnable. What if it learns the weight in such a way that it routes everything to first expert? All the tokens are routed to first expert. Then what will happen? I mean, the other GPUs are going to be idle, right? And this anyway, we don't want that, right? I mean, those are wasted parameters. So how should we avoid it? Any idea? Any guesses? How should we avoid router collapse? How should we do that? How should we ensure that each expert is used equally? Very good. If one is used more, add some penalty. That is called, have a loss function which penalizes skewed distribution, right? So that's called load balancing loss. We can design that, different papers design it differently. We can quickly look at one specific design which was used in switch transformer paper. So the idea is very simple. Let's say we have expert 1 to expert n and token 1 to token t in the batch, right? Now let us count how many tokens are getting routed to each expert, right? So let's say token j is routed to expert I, so this is 1 here, right? And then we can count, which other tokens are routed to token I, right? So here we will get f of I, which is going to be sum of this divided by t, number of tokens that we have, right? So this fraction is sum of this divided by t. The fraction of tokens dispatched to expert I is f of I, right? Okay, which is defined as this. And again, in the same graph, let's say I have expert I and I am looking at token j. What is the router giving me here? The router is giving me probability of selecting expert I given token j, right? And I want to compute probability of selecting the expert I. This will be equal to, this is the conditional probability time p of tj and summation, right? do we have P of Tj? We don't know, right? So and then you can look at it as, this is the probability times some value, and this is the expectation of, essentially this is, you can view it as expectation of P of Ei given Tj, right? Does that make sense? I mean, if you have to compute expectation, how do you do? Let's say you want to compute expected score, right? So you see how many students get a score of S1, you multiply it with that N1 times how many students get a score of score 2, N2, let's say, and divided by N1 plus N2, right? So this is probability of score 1, right? P of S1 times S1. This is P of S2 times S2. Similarly, if I have to compute the expected value of this term, that will be, we multiply with the probability and then this, right? And another way of computing this average score is going to be, if I can't compute the probability, how do we do it from a sample? I mean, right, so for example, here itself in the class, if we have to compute the average score, right? Let's say 5 students got a score of 10 and 15 students got a score of 20. My average is going to be 5 times 10 plus 15 times 20 divided by 20. Alternatively, I can ask each of you what is your score and keep a simple average, right? So that's how we estimate the probability, right? So similarly here, I have P of Ei given Tj for all j. I can take the average of these, right? So I can simply say P of Ei given Tj summation over j by 1 by t, number of tokens that I have. This gives me P of E, probability of selecting an expert. Okay, now, or P of I, probability of selecting an expert I. Now let's look at this loss term, F1 P1 plus F2 P2 plus Fn Pn. This is the loss term that they use for load balancing. Let's try to look at intuitively why it makes sense, right? Let's say F1 is very high. That means all the tokens were routed to expert 1. To minimize this, what should we do? P1 should reduce, right? So this should reduce if F1 is high, right? And because the probabilities are gonna sum to 1, P1 to Pn sum to 1, something should increase. And what should we increase without increasing the overall value? We want to minimize, right? This is the loss term, you want to minimize, right? Which one should we pick to increase without affecting the overall loss? Which has lowest score, right? So if this has the lowest one, we will increase the probability from here. We'll take the weight from here and give it to this. So that's how, I mean, to maximize this loss term, probability of those experts is getting reduced where we are allocating more, and probability of those experts is increasing where we are allocating less, right? So intuitively this will try to balance the load, and equilibrium will come at 1 by n, right? Okay, so we covered this part as well, where we are trying to add a new loss term to prevent router collapse, right? Expert collapse did not happen because of the nonlinearity. We saw that. The training time is in million GPU hours, and we have to exploit multiple GPUs. For that, we looked at various parallelism strategies: data parallelism, tensor parallelism, context parallelism, pipeline parallelism, and then today we looked at expert parallelism as well, right? Together they are called 5D parallelism, right? Then we looked at another graph where we were looking at the throughput versus the performance, and we observed 2 anomalies. First one was this, where we saw that this model has same parameter size but higher throughput, and we attributed it to its efficient implementation. So we looked at flash attention, which is the norm. We cannot train any model without flash attention, any meaningful model without flash attention, right? And then we saw that there are fused kernels for other tasks as well, and there is a library called Liger kernels and does it, right? That's what we looked at. Then this graph is about throughput, right? So throughput means inference. So we need to do inference also efficiently, and then we looked at standard techniques for efficient inference, starting with KV caching, VLLM, which is an inference serving LLM serving inference engine, which is very quite popular. Then we left flash decoding and speculative decoding for homework, right? And then today, we went back to our initial graph and focused on the second anomaly that we saw, which was that there are two models. One is quite bigger than the other, but still has better throughput, right? So how is it happening? And we attributed that to a better architectural choice, architecture design, better design, which is mixture of experts. And we looked at the inner workings of mixture of expert as a layer and how it is integrated in a transformer block. And then we also looked at why the different experts are not collapsing during training, and we also looked at how do we avoid the router collapse. And so this with this we can conclude this lecture series, where which had three parts to it. The first one was parallelism strategies, the second part was efficient implementation, and the third part was efficient design, architecture design, where we covered mixture of experts, right? So yeah, we can conclude here, and if you want, we can quickly go through the first block here, if that would help, because this is where we spent most of the time. We spent 4 lectures here. So let's very quickly recap what we were doing. Our objective was to train big models on big data. We saw that GPU memory is not sufficient. One GPU memory is not sufficient. To understand that, we looked at what lies in the GPU memory during training. There are 4 parts to it: model weights, parameters, optimizer states, and activations. We saw that these 3 are proportional to h square plus h. We have 12 of these and 13 of these per layer, right? This is small, but when we look at activations, this was big because of the self attention part. We, in addition to this h square plus h, we have sequence length times sequence length as well, right? And then we have number of heads times this and times batch size times 5, right? So the activations would typically look like a 3-dimensional tensor with batch size here, sequence length here, and the hidden dimension here. And in various data parallelism strategies, we tried to break this tensor across different dimensions, right? In data parallelism, we said that, okay, we will have one batch and we will process it on one GPU, take the second batch, process it on second GPU, and so on and so forth, right? And from where did the idea of this originate? This originated when we looked at gradient accumulation, because if we don't have multiple GPUs, we can repeat this DP times on a single GPU as well. And we also looked at the concept of gradient recomputation or gradient checkpointing, right? Where we said that if it requires so much space, right, let's not use it, let's not store it. The attention metrics that we get, after softmax, we decided to let go of it and recompute it again during the backward pass. We saw that we are able to get 70% speed up by increasing our compute by just 4 or 5%, right? Okay, then after data parallelism, we saw that when we parallelize the data, right, and you look at the different GPUs, there is a lot of redundancy there. We have the optimizer states lying on each of the GPUs. We have a copy of the model parameters on each of the GPUs, and we reserve some space for the gradient of each parameter as well on some GPUs, right? So we looked at sharding techniques, where we said that, okay, in the first sharding strategy, we said that we don't need the optimizer on all the GPUs. We shard it for each, let's say with dimension 0. For each layer, some parameters are going to stay on GPU 1, some parameters on GPU 2, some parameters on GPU 3, right? But if we are distributing the parameter, we will need communication, right? And now when we need communication, we try to overlap it with computation, right? So that's what we tried to exploit. Then we looked at 0 2, where we sharded, in addition to the optimizer states, we also sharded the gradients, right? Because once we use the gradients to update the optimizer, we don't need to reserve the gradient for each parameter on all the GPUs. We can reserve some space for the corresponding parameters that we have on the optimizer, right? Temporarily allocate the memory for a particular layer for all the weights in that layer, right? For the gradients of all the weights, compute the gradient, right? And then transfer a part of it to wherever the corresponding optimizer lies and store it there, right? And then in the third part, we sharded the model weights as well. But then if you are sharding the model weights, how do you do a forward pass? Well, you gather, right? So because you have to gather, that increases the communication cost as well, right? So these are the three data parallelism and fully sharded data parallelism strategies that we looked at, right? But this is still not good for big models and large sequences. And then we looked at splitting the activation across GPUs, right? So earlier, again, batch size, sequence length, and we have hidden dimensions. The data parallelism is split this. Now we will try to split the hidden dimension, right, in tensor parallelism. For example, in the MLP layer, we have the inner, the up projection projects H to 4H, and we saw that we can keep each of these separately on 4 GPUs, right? And for the attention block, we said that there are multiple heads, so there's a natural way of splitting. We can keep each head on a separate GPUs, but this will again increase some communication cost, right? While looking at tensor parallelism, we saw that so again, in tensor parallelism, we have the same input, right, but different computations on different GPUs. First GPU is computing these neurons, second GPU is computing these neurons, right? So same input, different neurons. We are able to parallelize MLP layer and attention, but then we have layer norm and dropouts, right? So we thought that in addition to this, we can introduce sequence parallelism, where once we gather the output from different GPUs, we can scatter them across the dimension of the sequence length. So sequence parallel is parallelizing across the third dimension that was left, which is the sequence length. We use the term sequence parallelism only in conjunction with tensor parallelism, right? There is right now, all of this is good, but still this is not sufficient if we have very large sequences, right? So if you have very large sequences, then we can take motivation from sequence parallelism and devise something called context parallelism, where different GPUs will have different parts of the input sequence. So this is X1, X2, X3. This is subsequence 1, subsequence 2, subsequence 3 of my input X, which is concatenation of these three, right? We split the model vertically, right? We say that X1 will be processed on one GPU, X2 will be processed on another GPU, X3 will be processed on the third GPU. But now, both the GPUs here are doing the same computation, same MLP, right? Same computation on different inputs in some sense, right? Does that make sense? Right? Now, but the issue here is that self-attention needs to communicate. X1 has to attend on X2 and X3 as well, right? And to address that, we studied ring attention, which was similar to the block attention that we looked today as well, right? So to handle the attention which is split on multiple GPUs, we look at ring attention, and then here we observed that the communication overhead beyond a node was prohibitive. That on one node we have 8 GPUs. Communication is very fast there between those 8 GPUs, but in tensor parallelism, same input is being computed at different in different GPUs. We have to combine the results before passing it to the next layer. Right, so there's a lot of communication overhead. We cannot split beyond a node. So what should we do? For that, we looked at pipeline parallelism, where we create a pipeline of the model, essentially. Right, we have first few layers on one GPU. All the activations for those layers lie on that GPU. Let's say layer 1 to layer 4. The activations on the layer 4 are passed on the second GPU. But there we saw that because of the pipeline, there is a lot of wastage. GPUs are sitting idle, and then we looked at various scheduling techniques, right, and allocation. How should we allocate the layers to each GPU, and how should we schedule? Looked at one forward, one backward, for example, right? And then we also looked at in the end where we said that we will have first few layers on GPU 1, and then again the last few layers on GPU 1. Right? The whole idea is we want to quickly do my work and give the output to the other, because the other guy is waiting for me. Right? So instead of having layer 1 to layer 4 on one GPU, I have layer 1 to layer 2 on one, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the 9, 10 again on the GPU 1. Right? So this is with this we concluded the parallelism strategies. Okay, again some homework for you guys. Now with all the background that we have covered in these 6 lectures, you should be able to understand all of these papers, because mostly these mixture of expert models are big models, and to train them you need multi GPU training and parallelism. We have already covered that, so you should be able to understand all these 3 papers. Right? Yeah, so that's all. Good. Thank you.